Are more than cosmic puzzles. They are also mirrors reflecting how we innovate, cooperate, and carry scientific responsibility. They also remind us of a simple truth. Discoveries rarely happen in solitude. They are built by teams across labs, languages, and time zones, which stitch together ideas into insights, like stars that only take shape in a constellation. Perhaps the most beautiful paradox of space exploration is this: the farther we look outward, the more we should discover inward. Our values, our methods, our capacity to be wiser together than alone. International space law treats outer space as a shared endeavor, not a playground for a few. The Outer Space Treaty mandates exploration for the benefit and in the interests of all countries, affirming space as a province of all mankind, with free scientific inquiry and non-discriminatory access. So states are responsible for national space activities, governmental or private. So public rules and oversights are mandatory when private actors go to space. At the same time, we must be candid about today's headwinds: unilateral norm setting and a first-come, first-served logic around resource extraction. Increasingly powerful states and also private actors shape access to space, risking a drift away from the global common ideals and the space treaties. The capital markets reward scale and speed. Products of these companies increasingly function as critical space and terrestrial infrastructure. Dominant network effects can entrench gatekeeper positions in launch, data, and downlink services. Moreover, the dual-use reality makes commercial operators targets in conflicts and pushes into quasi-sovereign roles. Especially when access or prioritization of services follows unilateral corporate or national preferences, we expose ourselves to the risk of norm erosion. Launchers, satellites, and data are inherently dual-use. Commercial constellations now provide battlefield connectivity, navigation, augmentation, and imagery. Boundaries between civilian and military use are blurring, potentially increasing escalation risks. When private assets influence national security, emergency response, and global connectivity, decisions cannot rest in a single corporate boardroom or in CIO's social media feed. Fair access and non-discriminatory terms are prerequisites for space to remain global common. Global South wants the voluntary exclusive arrangements deepen inequality and calls for binding, inclusive governments to guarantee fair access, benefit sharing, and sustainability. Otherwise, the promise that space serves all humanity is undermined by national interests or commercial competition. In other words, capitalist power, politics, and nationalist protectionism undermine the very logic that space should benefit all. Safeguarding the common requires democratic oversights, transparency, and solidarity by design, not by afterthought. And it requires co-creation, setting standards together, sharing data openly, and building capacity so that more nations and disciplines can meaningfully participate. The Queen's Lecture, hosted with the British Embassy and British Council Germany, stands for the bridge between wonder and workmanship, between countries and disciplines, between discovery and impact. Our theme, Cosmic Origins and Alien Worlds, the next area of space exploration, highlights two landmark missions. Euclid, now delivering first data after 2 decades, maps the universe geometry to probe dark matters and dark energy. NASA's Habitable Worlds Observatory aims to detect signatures of life on distant exoplanets. These efforts demand breakthroughs in optics, detectors, and data science, whose effect reach far beyond astronomy. What does it mean for us as TU Berlin? We share this bridge-building spirit in concrete ways. Before we look up, let's look around. For most of us, space feels distant. Out there, not here. A far horizon rather than a daily companion. Yet the orbit is quietly busy with systems that shape our everyday lives. Navigations for planes and ships, timing for banking transactions, Earth observation for weather and climate, connectivity for logistics. When satellites falter, everyday conventions falter too. Aircraft lose optimized routing, ships face navigational risk, payments struggle to synchronize, and even the pizza delivery may miss our door. We might smile, but this point is serious. Satellite networking are the quiet helpers of modern life, and precisely because we depend on orbit-borne data, they have become the thread that binds the fabric. Pull it, and the weave loosens. Resilience here is a team sport. Engineers, cybersecurity experts, policymakers, operators must coordinate across borders and sectors to keep the lights on, the planes routing, and yes, the pizza driving. While large-scale missions chart the heavens, our university has shown that innovation also thrives at smaller scales. With 32 successfully launched and operated small satellites, TU Berlin demonstrates that spaceflight advances not only through flagship, but also through agile, efficient formats. So that's the proof that big and small are not opposites, but complementary routes toward the same idea. Before we are opening the event, let me highlight that science is a teamwork, especially tonight. So my special thanks goes to our British and German partners, the British Embassy and the British Council Germany, to our TU Berlin organization team, and to all who made this program possible. And of course, I also want to thank you, the audience, with your questions, your perspectives, even your constructive disagreements. This keeps science vital. This partnership and the Queen's Lecture itself remind us what can be achieved by working side by side. Our questions of cosmic origin or quest for life are met best not by a single nation, but by open hands and open minds. So tonight, as we look up together, let us also thank our British colleagues and the legacy of the Queen's Lecture for sustaining a tradition of scientific exchange, curiosity, and shared discovery that inspires Berlin and the world. Thank you.
Madam President, Mr. Ambassador of the United Kingdom of Great Britain and Northern Ireland, ladies and gentlemen, students, it's both an honor and a great pleasure to speak welcoming words to the Queen's Lecture 2025 here at the Technical University in Berlin. Some of you may be very disappointed that you don't see the Federal Minister here, but for me, it's a great pleasure. 6 months ago, it's today actually 6 months ago that we took office and I became the Deputy Minister and the first Space State Secretary. So I wouldn't have dreamt about this when I was a teeny boy and observed sunspots in a very small observatory close to Heidelberg. But sometimes dreams come true, and that's great. So together we gather not only to celebrate the legacy of the extraordinary leader, Queen Elizabeth II, but also to look towards the future. Spaceflight has become part of our everyday lives. For phone calls, car navigation, weather forecasts, emergency services, and climate monitoring. Without space technology, our modern way of life wouldn't work. But spaceflight is more than just technology. It's an expression of our curiosity. When I, for the first time, met one of our first astronauts, Ulf Merbold, he explained to me, it is in our genes that we want to explore. We explored new continents, we explored the sea, and now it's space, it's the moon, it's Mars, and the final frontier. And we drive to explore, and our urge to answer the big questions is, where do we come from? How did life begin? And what lies beyond our horizon? To find answers, we reach for the stars. And this ambition drives enormous innovation. You spoke about it. Spaceflight forces us to develop technologies that don't yet exist. Look at the layer on my glasses that prevent scratches. That comes from the moon flights in the late 60s and 70s. And now the technologies make things more precise, more robust, and more powerful than ever. That only works when science, research, and industry work hand in hand. Universities and institutes bring the ideas. Companies contribute with their expertise in sensors, IT, artificial intelligence, or materials. And in the end, we all benefit as a society, as an economy, as future shapers. These projects also create opportunities for young people. Many of them I see here. Someone working on a space project today might work at a tech startup tomorrow, contribute to climate research, or develop the next generation of spacecraft. Space is a powerful driver of innovation far beyond space itself. Such projects only succeed together. Missions like Euclid, Pepe Colombo, Plato, or JUICE show no country can do this alone. That's exactly why the European Space Agency, ESA, was created, a European success story that turns 50 this year. At the end of this month, November, ministers will meet in Bremen at the ESA Ministerial Council. There, key decisions will be made for the future of European space, especially for science programs far beyond 2025. What makes me especially happy, Germany and the United Kingdom are working closely together. Just yesterday, I had an intensive meeting with Baroness Minister Liz Lloyd, who is responsible in your government for space. And we talked about LISA, which is a great example for our cooperation. It's the first gravitational wave observatory in space. A truly exciting mission, though we will need to be patient for at least another decade to see the first results. But projects like this already show today Europe is not just a partner, but a co-creator of international space exploration. Around half of the James Webb Space Telescope's instruments come from Europe. That's not a footnote, it's a proof of technological excellence and trust in Europe's capabilities. And I just got the confirmation that I think there is no other university in Germany that has built so many satellites than the Technical University of Berlin that fly now in space. What was the number? 35 satellites. That's really a great success story of this university. That's something you can really be proud of. Wonderful. But the view up starts down here. As I just said, our universities and research institutions, and this university is a great example. So thank you for hosting this event. Thank you, dear guests, for being here. TU Berlin shows how curiosity turns into real achievements. There are other examples. Nano, FF, and the InnoCube test new technologies in orbit. Tubin detects forest fires from space, and new missions to the Moon, Venus, or asteroids are already in preparation. This project shows what's possible when passionate people research, create, and take responsibility. And that's exactly why the federal government has created the new Federal Ministry for Research, Technology, and Space, the Ministry of the Future. We want to bring space policy together, make it strategic, and ensure that Germany and Europe can act in an environment of growing global competition. Because if you are too late, you lose ground, even in space. Ladies and gentlemen, exploring space, as I outlined, is a deep human instinct. It speaks of our courage, our will to understand, and our belief that progress is possible. Big words in a small room, here and now. So all that is left for me to say is I wish all of us great success on this shared mission, because spaceflight is not an end in itself. It's a promise that together we can push the boundaries of what's possible and go together where no one has gone before. Thank you.
So good evening, everybody, and thank you very much indeed to all of you that have chosen to spend this portion of your afternoon with us. It is a particular honour to be able to welcome you to this year's Queen's Lecture. What an exciting topic we've chosen to talk about, for all the reasons that Professor Rauch, the State Secretary Plyer, has talked about so far this evening. We're broadening our horizons, we're looking to the future, and we're looking also to the relationship that we have between Germany and the United Kingdom in a sector that offers so much possibility. So this is a historic milestone, I'm bound to say this evening, the 60th anniversary of this distinguished series of lectures. And that is, I think, prompt enough to reflect a little on the history of this proud event. The Queen's Lecture was established in 1965 to commemorate Her late Majesty Queen Elizabeth's state visit to Berlin. And really, from its inception, the lecture has been a co-production, I'm very pleased and proud to say, between the Technische Universität Berlin, the British Council, and the British Embassy. It was set up initially as a platform for a leading British scientist to share insights and indeed discoveries with a Berlin audience. and to foster that fabulous British-German relationship in science and innovation, a partnership that has long played a significant, and I would say today growing role in advancing progress. The inaugural lecture was delivered in 1966 by Dennis Wilkinson, an experimental physicist from Oxford. In 1997, it was revived to coincide with the 50th anniversary of the TU Berlin, and since then the TU has graciously hosted each year, offering a stage for a wide variety of speakers. I think it's probably fair to say a particularly memorable moment came in 2015 when Her late Majesty and the late Duke of Edinburgh attended the 50th Queen's Lecture during their final visit to Berlin, where they were warmly welcomed by the President, Joachim Gauck, and by Chancellor Angela Merkel. And I'm really pleased to say that this year's lecture continues that proud tradition of promoting scientific excellence, and we are really privileged to welcome Professor Adam Amara, distinguished astrophysicist, head of the School of Mathematics and Physics at the University of Surrey, chief scientist at the UK Space Agency. More shortly from the professor, who will begin, so I understand, and if I'm wrong on this topic, we'll find out in a second, by exploring the bold ambitions of the European Space Agency, by NASA, before turning to two visionary missions. The European Space Agency's Euclid, a project to explore the dark universe, and NASA's Habitable Worlds Observatory, the next flagship project to search for signs of life on distant exoplanets. And closer to home, the United Kingdom has, like Germany, become a dynamic force in the global space sector, blending a proud legacy of scientific discovery with cutting-edge innovation and international collaboration. And I see this from the role that I occupy here today. This is a sector and a collaboration that genuinely matters. Germany and the United Kingdom are key partners in this journey. In July, I'm delighted to say, we signed our first broad-based, comprehensive bilateral treaty, the Kensington Treaty, an agreement, permanent agreement between the two nations to work side by side across the breadth of our bilateral relationship, but on the strategic technologies also that will shape our tomorrow. Amongst them, space stands out as one of the most exciting in terms of scientific and technological discovery, but also the potential for future economic growth. The global space economy, already worth 550 billion euros in 2024 and expected to double by 2040. And as the UK develops multiple spaceports, we're working closely with our German partners to help ensure that launch becomes a reality. In 2025, the German rocket factory Augsburg received the UK's first vertical space launch license, marking a genuine turning point for European space innovation, with the orbital launch from UK soil expected in the coming period. And this forms part of a much broader collaboration across space. The UK Space Agency recently announced 5 new international projects with German counterparts worth over £1.2 million, a powerful example of the modern Anglo-German relationship built on research, technology, scientific collaboration, just as was envisaged by Her late Majesty the Queen 60 years ago. Before Professor Amara takes us on a journey into that future of space collaboration, I'd like to extend my very sincere thanks to Professor Rauch and her team for the outstanding organisation, once again, of this year's Queen's Lecture. I want to also thank the British Council colleagues and colleagues also from the Embassy for their invaluable support. Until 2019, Her late Majesty traditionally sent a message to accompany the lecture. Sadly, this tradition was interrupted by the pandemic. I'm therefore especially pleased that in honour of the 60th anniversary of this distinguished tradition, His Majesty the King has sent a message, which I now have the honour to read out to you. And the King has said, "I wanted to convey my very best wishes to you all as you mark the 60th anniversary of the Queen's lecture. It is most heartening to know that my late mother's gift of this lecture series to the city of Berlin in 1965 continues to serve as a lasting symbol of our nation's shared leadership in science and technology. The anniversary lecture delivered today by distinguished astrophysicist Professor Adam Amara will touch on the themes of space science and research. I know that you will be all too aware of the profound importance of these areas, not only in advancing our understanding of the world we live in, but also in driving innovation and expanding our capabilities in the Weltraum in a way that is truly sustainable and respectful of the space environment." And the King concludes by saying, "I hope you all have a most inspiring and enjoyable evening, and I wish all of you who play a part in hosting the Queen's lecture every success in the years to come." Thank you.
Thank you very much for these wonderful introductions. Mr. Ambassador, I'd like to say that to acknowledge His Majesty the King's leadership in understanding the importance, as the President said in her opening remarks, that space is this common. And very often with the commons, we find that if we don't take care of it, we will end up with a lot of problems. And so what I'd like to do today is present to you a vision of what space can do. What I'm hoping is that I'll talk about an inspiring part of how we can understand the universe, how we can look for alien worlds, and underneath all that, I'd like to tell a story about technology. And I'd like to take away two things. If I've done this right, what you'll see is an accelerated rate of progress towards important questions. So questions that are deep in our humanity around where do we come from and are we alone? And recently we've been able to grapple with these problems with greater and greater speed in a way that would have been unimaginable in the past. And I'm going to put that down to technology, and hopefully you'll see that. But I think it also works the other way. Innovation, we talk a lot about innovation and the need for the economy to have innovators, but innovation is a weird thing. It doesn't happen in a 9 to 5. It doesn't happen in a structured way. In my experience, to do innovation, you need passion, you need to be excited about a topic, you need to be obsessed about a topic. And what I found when I travel the world is a lot of people get excited about the cosmos. And so one way to look at innovation is how can we take that deep human enthusiasm about cosmic origins and alien worlds and questions of that type, and how do we channel that into building better technologies to not only tackle these questions, but also build better societies, better technology, and help in all manner of ways. To set the scene, what I'd like to do is create a timeline of where our understanding of the universe has come from. I'm not a historic anthropologist, so I'll tread lightly on the early history of humanity. But it seems to me that when we look back thousands, tens of thousands of years into our history, we find evidence in our structures, in our cave drawings, that the stars and the heavens have been important to us as a species. They've been important for us for telling the time, they've been important for us to navigate, and they've been important for us, as we know from oral traditions that date back thousands of years, about deep questions about where we come from. Today, things aren't completely different. You know, the more things change, the more they stay the same. Our ability to navigate now requires, instead of natural stars, they require human-built satellites to connect with our Google application, Google Maps, to get us around. So we still navigate from space. We manage our timings in financial transactions now because of artificial satellites. You know, so we don't need it for the seasons, but we do still need precision timing. And we still go back to the same questions of our cosmic origins. So to set the scene, rather than go through all of human history, I think we can go back to, say, Aristotle and Ptolemy, where the universe was seen as the Earth in the center and a celestial sky that was static and infinite in every direction. And we have to move well into the future to start to get an understanding of the cosmos that looks like what we know. And what I'd like to highlight is this Copernican revolution. The Copernican revolution took this idea that dates back to early days of us at the center of the universe and did something radical. It shifted us. And this was a combination of work by Copernicus, Galileo, and Kepler, all great thinkers of the time. And that idea that Earth, us, we are no longer the center of the universe, and they put the sun at the center of the universe, is the underpinning to how we see our modern cosmology. We call it the Copernican principle. It's also known as the cosmological principle. But it's the idea that the universe does not have us at the center. And that, again, was a radical idea in human history. Jump forward 170 years, and we begin to enter a very interesting era. So, whereas in Copernicus's day, the universe was seen as mechanical, Newton did something incredible. He came up with this idea of a universal gravity. So the idea that the rules that govern how we operate on Earth don't stop here, but they extend out into the heavens. So the orbits of planets and all of that can be connected mathematically together in a unified gravity way. And again, another huge advancement in our understanding of the universe. But it's also an uncomfortable theory of the universe because gravity in Newton's day struggles with infinities. And we were all convinced that an infinite static universe was what we lived in. Jump forward 160 years, and we can already see what I find really interesting is simple observations can sometimes have profound implications. The simple observation here, which is attributed to Oort, but dates back even further, is the night sky is dark, which seems very simple. And I was talking earlier, sometimes the questions that children would pose turn to be very fundamental. And understanding why the sky is dark in a Newtonian universe that extends forever is actually really hard. And there are many ways that you can show this mathematically, but the easiest way to think about it is in an infinite universe, if you look out in any direction, eventually your line of sight will hit a star. That means that every direction in the sky should be as bright as a star. So, in the universe of the time, the night sky should be very bright. And in fact, it is dark. And that is a serious problem. And bizarrely, the solution to this problem was put forward by the poet Edgar Allan Poe in his poem Eureka. And the solution, which you can work through and is presented much more poetically than I would say, boils down to the fact that the universe is finite. So you can't go back forever. And as soon as you put a bound on the universe, you solve the dark sky problem. So already, again, we've taken it for granted, but it took a long time for people to get on board with a finite universe. But then we have to jump even further. To enter the modern world of cosmology, where we can solve problems on universe scales, we need a general relativity. And this, of course, Einstein provided when he invented space-time and the idea that gravity bends space-time and objects move in response to how space-time is bent. An incredible achievement in our knowledge of understanding how the universe works. And with these equations, we could solve the complete system of how the universe evolves in a way that we never could with Newtonian gravity. And then we entered this incredible period as we went into the middle of the 20th century. Physics was at an absolute high. We had gravity, bending of space-time. We had moved all the four forces of nature, all the forces of nature into four fundamental pillars. We understood them to be gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. Everything in physics falls under one of these umbrellas. And they get stronger as you go to the right. So the strong nuclear force is what keeps the nucleus together, keeps the proton a proton. The weak nuclear force is what allows nuclear particles to change. The electromagnetic force is what keeps atoms together and what drives a lot of what we talk about. And gravity is the force that keeps the universe together. Of these, gravity is pretty weak, right? So if we pick the weakest of the other three, electromagnetism, you might come up with a simple experiment. Imagine taking a magnet and putting it over a paper clip. The paper clip will jump up to the magnet. That paper clip is being pulled by a tiny little magnet, which wins, and the entire Earth, which loses, right? So you might easily assume that gravity is a fairly weak force compared to the others. However, when it comes to doing universe work, gravity is phenomenal. Gravity is phenomenal because it is the only one of these forces that doesn't cancel out. The technical word is shielded. It doesn't cancel out. So when we look at our sun, for example, as an illustration, the sun is doing all kinds of nuclear forces. It is pumping out incredible radiation in the electromagnetic spectrum to the point where we can't look at it and it powers life on Earth. It's very easy to think that that is what the sun does. Take a step back, though. Think about the sun in a different way. Think about the origins of the sun. The origins of the sun are a ball of gas. The ball of gas gets pulled together by gravity. Gets pushed and pushed and pushed until it becomes really hot. And for a brief moment in its history, billions of years, the other forces work together to resist gravity. And they will do that successfully for billions of years. But they will lose. They will lose because eventually gravity will win and gravity will collapse our sun. And that is the story of the universe. If you want to understand the universe, you need to understand gravity. So let me take you back to the mid-20th century. By the mid-20th century, we physicists felt great. We'd managed to unify three of the forces into what's called the standard model of particle physics. And the next thing was obviously combine it with gravity, with maybe a quantum gravity theory, and the job would be done. How incredible that would be. There were niggling things that we already knew about. So this is the famous physicist Fritz Zwicky, who observed this object, the Coma Cluster. So the Coma Cluster is a collection of galaxies, thousands of them. And what Zwicky did was look at all the galaxies, look at how fast they were moving, and realized that the system didn't make sense. It didn't make sense because if he added up all the mass that he could see, and if that mass is keeping the galaxies together, it would fail and all the galaxies would fly apart. But yet, they ended up bound. So he coined this term, dunkle materia, which has now stuck. And this is our dark matter. But other than that little wrinkle and maybe a few others, we were well on our way in physics in solving the problems. And notice the time steps have gotten shorter, by the way. That wrinkle of dark matter through the 1970s started to become a real problem for physics. So this is Vera Rubin. What Vera Rubin did was look at the stars in this galaxy. This is M31. And she could accurately measure the velocities of all of the stars. And there you could see that the galaxy was rotating. But the stars were rotating much faster than would be allowed by normal dynamics. And the only way to explain it is that that galaxy sits inside a large amount of dark matter. And over that decade, one piece of evidence after another came in that just introduced this weird material, dark matter. We're now able to compute. We don't know what dark matter is, but we can compute what it'll do with great accuracy. And what dark matter would do, if it starts off in the universe as quite small, is as the universe evolves, it forms what we call a cosmic web. With galaxies would sit then in the middle of these nodes of the cosmic web. So we know how dark matter would evolve. We have no idea what it is. But that was the 70s. Let's move on to the 1980s. Surely things get better. They don't. They don't at all. We end up with a problem at the other end of the universe. So it turns out, and if you have any questions, I'll go through the technical details, but it turns out in order to understand what we knew about the universe, the very early universe, right after the Big Bang, almost in an instant, had to go from teeny tiny to absolutely massive, and then grow in a way that you can barely see on this diagram. This is the only way we can explain the data, is an almost instantaneous, rapid expansion that took the universe from a quantum scale to a cosmic scale. We don't understand it. We've given it a name. We've called it inflation. But it's still an area of the universe that we don't understand very well. That's okay. That was the 80s. The 90s. I remember the 90s. Another problem appeared. This one then had to do with the way the universe expands around us. Until the 1990s, we thought of the universe as a giant expanding system pulled under its own gravity, and anything that's pulled under gravity will slow down. So it was all about how much is the universe slowing down, which turned out to be completely wrong. The universe, for the last few billion years, so what you can see here is the universe goes through that weird inflation thing, and then it starts to slow down, and then a few billion years ago, it starts to get faster. Okay? This has now, and the interesting thing is you read the literature from the 90s, and we were adamantly against this, even though the evidence kept pointing in this direction. And eventually, by 1999, we gave up. We accepted the universe is doing this acceleration. A Nobel Prize was awarded for that nail in the coffin. And we've had to understand what that dark energy is doing. So, what does that mean for our journey across the universe? Well, the 20th century was an incredible time for physics. Halfway through, we thought we'd done it all. We thought we'd almost got it all together. And then we ended the century by not understanding 95% of the universe. Right? Brilliant. Dark matter. Dark matter is a substance that exists in the universe. We don't know what it is. If it's a particle, it could be the smallest particle ever detected. It could also be particles 20 times bigger than our solar system. Dark energy is causing our universe to accelerate ever faster. We don't know what it is. If it's a substance that would have something called the equation of state parameter that's weird compared to any other substance we know. And inflation remains a mystery. And I think one of the things that we need to keep in mind is that for each of these problems, the standard model, so the three forces on the left-hand side, have offered up solutions. For inflation, they've come up with something called a quantum field, an inflatron. And they're like, don't worry, we can do this. For dark matter, standard model says it's just a particle we haven't detected yet, we'll find it, and yet they have struggled to find this particle. And for dark energy, again, they offer up a quantum field. It's a very awkward sort of quantum field. So when you think about dark energy, from the standard model, you're happy with a very big dark energy, or you're happy with zero, but this awkward low level that we have is a real problem. So those are the three solutions that are offered by the standard model. Now, we will see how this mystery evolves. Now, for me, it's really strange that these three cosmic problems don't have a gravity solution. And there are plenty of people out there working on possible gravity solutions to one or two or three of these areas that we don't understand. So how do we make progress? And my answer, I think, is technology. Technology is what pushed our understanding at an accelerated rate. Technology is what got us into this mess of not understanding the universe, and I believe it's technology that's going to get us out of this. And in particular, I'm excited about the Euclid Space Telescope. And hopefully I can show you an animation. So the Euclid Space Telescope is an ESA mission. Here it is. It was launched in 2023 after 20 years of development. It moved very far from the Earth and is going to survey with phenomenal accuracy a huge amount of the galaxy. What you're looking at here is one of the best digital cameras ever built by humanity. When it comes to the ability to take a panoramic picture with incredible zoom capability, we as a species have never built a telescope like this. To do that, we had to solve problems around stability. How does a telescope like that, after 6 years, perform the same at the end as it does at the beginning? How does it not wobble as the observations are taken? How can you fit an enormous camera onto a telescope like this? And we solved those challenges and got this telescope out there, and it's collecting data. And so to give you some dimensions, this is a 1.2 meter telescope. So light comes in, bounces off the main mirror, goes up, bounces off a secondary mirror, and then goes down and goes into this channel where the work happens for imaging. It is a collaboration involving dozens of countries and thousands of scientists. The instrument design was world-class, the instrument build was world-class, and the analysis of the data, again, you can imagine the world's biggest digital telescope working full-time for 6 years produces a huge amounts of data. That is a real challenge that we're working on right now. And what I'd like to show you very briefly, since bridges were brought up between countries. So this is the telescope upside down. This is the main telescope. And as I said, light will come in here and enter here. The light then gets bounced around and hits this thing, which is called a dichroic. The dichroic splits the light into visible and near-infrared. And the near-infrared rays go into this NISP camera. That digital camera, which measures the infrared, was built between Germany and the US and brought together here as part of this ESA project. The visible light bounces here, goes into this Viz camera. Again, this incredibly accurate digital camera. That camera was built by UK and France working together. So each instrument has a bridge, and then they were brought together to do this world-class measurement. So what will it actually do? In order to test dark energy and dark matter, these subtle effects, it turns out you need to measure as many galaxies as you possibly can. Euclid is very hungry to measure every galaxy in the universe to high precision. So one of the immediate challenges is we sit in the middle of the Milky Way, so what we see here, all of this beautiful structure is our galaxy. And as much as I love our galaxy, when it comes to understanding dark energy and dark matter, this is a pain. And so Euclid will survey everything else, as much area as we can get outside of our galaxy. It'll also survey areas very, very deeply. So we'll get a pass of as much of the extragalactic sky as we can get, and we will do a survey of the middle. It's a 6-year survey, so this is going to take a while. But we have already released, so this is again another view of our galaxy, this time with the Milky Way in the middle. We have already released the Quick Release Data 1. Quick Release Data 1 is this area here. And what we can do, so we released that in March of this year, and what we can do is we can zoom in, and that's what the current release of Euclid looks like. So it was released in March. It measures 63 degrees, which makes it only 0.5% of the full survey. Already within that 0.5% of the full survey, we've measured hundreds of thousands of galaxies, and we're starting to see the unique capabilities of Euclid in areas beyond what it was designed to do. And the capability is the needle in the haystack. Because Euclid is so stable, because it takes an image of everything, what you can do in post-processing is look for the weird objects in the universe. And you can look for the weird objects, and in the past, you needed to survey the sky and then find a potential weird object, go to another telescope, the Hubble Space Telescope, have Hubble look at your weird object to confirm whether or not it's an interesting thing that you care about. Euclid does the full panorama, and because it contains the resolution at Hubble levels, you can just zoom in. You don't need to call anybody else, you just zoom in. So when you take that area of sky, sorry, I need to be a bit closer, and you zoom in, you start to see incredible features. And so all of this structure contains information. And if you notice, say, over here, this one little thing is interesting, you can just zoom in. And you can get this kind of level of detail. This is something known as a strong gravitational lens. What's happening here is you have a galaxy in front and a galaxy almost exactly behind it. And what happens when two galaxies line up perfectly one behind the other is that the light from the galaxy behind bends, because as Einstein told us, gravity can bend light. And when it bends, it creates these weird images. So you see image 1, 2, 3, 4. That's the same galaxy, but it's been distorted. This is an effect that anybody that likes a glass of wine has seen regularly, and maybe you haven't realized it. But the bottom of your wine glass, as it tapers out, has this optical feature. So when you put a wine glass down on a pattern, you can look and see what a strong lenses system would look like. It's doing the work of a galaxy. But by having this resolution, these are very rare objects, because you need this chance alignment. By having these rare objects, you can study this galaxy in detail. The bending that's causing this effect is mostly coming from the dark matter. And so by understanding the bending, you can understand dark matter. And what you want is as many of these systems as possible. Within only a few months, Euclid has gathered almost as many strong lens systems as all data that came before. And by the time it's done, it'll be the greatest archive of strong lens systems that we've ever had. And that is a byproduct of what it does. The same is for other rare objects we might care about. So a lot of people care about quasars. Anything that's needle in a haystack, Euclid will do phenomenally well. But what it was designed to do was test dark energy and dark matter. And so I'll just flag the future result that you should keep an eye out for. We plan our first cosmology release in October of next year. The thing to keep an eye out for, and you never know where discovery is going to take you. You never know, right? What you might want to keep an eye out for is W equal to -1? I know this doesn't mean a lot to you, but it's a big deal. It's a big deal. So if dark energy is a substance, if it were a substance, it isn't, but if it were, we might want to look at its pressure and its density. The ratio of pressure to density is this thing called the equation of state. An equation of state of -1 is what Einstein's cosmological constant, the very natural thing you'd put into general relativity, would tell you it is. W is equal to -1. The problem is, most of the alternative theories for what dark energy could be also allow for W equals -1. So as we measure -1 for this number W, it's very hard to distinguish between alternative models. If W turns out to be not -1, well, first of all, Einstein's constant is out of the window. We have a dynamic universe and a dynamic dark energy. And then its precise value will tell us an awful lot about where to look for what this weird substance is. And when we were designing Euclid, this was the target. We designed the entire experiment to be able to measure this number to a precision of 2%. And there are hints that maybe we're seeing a dynamic universe. So there's an experiment called the DESI, which measures the spectrum of millions of galaxies. And they're starting to see evidence at the 3 sigma level that maybe W isn't -1. So in October, if that comes out, you'll be well placed to understand why that's a big deal and understand that there's a committee in Sweden who'll be mulling over that result with great interest. But Euclid is only one of the great experiments that ESA and Europe have led. Euclid forms part of our cosmic observatories. It sits here, right there. And what we see down here is our legacy experiments. So this isn't something new to us. It's something that we've been doing for a long time. And I think as Europeans, we can be very proud of the legacy, the contributions to human knowledge that we have made, and the technologies that have driven these. Up here, you can see that Euclid sits as a family of telescopes currently in orbit, currently looking very deep into the cosmos, all of them working in different wavelength ranges, from the sub-millimeter all the way through to the X-ray. And as we heard, the ministerial, and I'll see you in Bremen, I guess, we will look to the future and understand how we can support our new observatories. And in particular, LISA over here doesn't even sit on the electromagnetic spectrum. It's doing a measurement of space-time itself, which is revolutionary. So, we've talked about the universe. I'm excited about the universe, but I did also promise you alien worlds. So let's spend a few moments on where we go next with alien worlds. For this, I've shown the proud tradition that we have in Europe. I'll look now at NASA, and in particular, a subclass of the national missions called their flagships. So these are typically $10 billion level missions. They are enormous, but they are well known and famous. This is the Hubble Space Telescope. This is the James Webb Telescope that we heard about. The next one to fly is Roman, which is the US equivalent of Euclid. working in a slightly different wavelength. It'll be highly complementary. But the flagship that's being designed now is this one here, called the Habitable Worlds Observatory. And it's an audacious mission because we currently don't have the technology to do it. And as I'll explain in a minute, the problem is that in order to see a planet, you need to remove 10 billion photons from the star. And at the moment, we as a species don't know how to do that. But we think we can get there. And so we should start that journey. And before we understand why that's important, I want to talk to you about exoplanets, and we're back to the 90s. So when I was growing up, before 1995, we only knew about the planets in our solar system. I grew up knowing that there were 9, Pluto got demoted later, but that was the suite of planets that we knew about. 1995, Didier and Michel found 51 Pegasi b. This is the first planet that we as a species found that orbited another star. Here's how it compares to Jupiter, and here's how the star of Pegasus compares to our sun. This is the first planet of a comparable sort of stellar system. And of course, they won a prize for that from the Nobel Committee. And as we progress from 1990, which wasn't that long, 1995 to now, which again, for me, doesn't feel like that long, we've made a lot of progress. And there are, for this presentation, I'd like to focus on basically 3 main ways that we've discovered planets. One is called radial velocities. So it's easy to think about the star and the planet orbiting the star. That's the mental image that most of us have. The reality, though, is that they both orbit each other. They orbit what's called the common center of mass. So while the planet goes around, the star also goes around the common center of mass. So the star wobbles because of the orbit of the planet. And that wobble, we can see the star go forward and back. There's a Doppler effect, and we can measure that. And that's the measurement that Didier and Michel made. And since that discovery in 1995, we've measured of order 1,000 planets. We found them in this way. The other way that we can look for planets is if we're lucky and the planet goes right in front of the star, it blocks out some of the light. And so the star will get a little bit dimmer and then back up again. And now we've found thousands of planets like that. But maybe an even more exciting technique is to see the planets directly. And we've got techniques now where we can look directly at a star, remove its light from very advanced optical techniques, and then begin to see an image of the planet. And then we've got to the point now where we can see these planets orbiting around the star. So we see planet 1, 2, 3, 4. Over the years, we can see the orbits happen. And so this is a very exciting technique, because once you've got light from the planets, you're going to be very tempted to measure the spectrum of the light from the planet. And once you've got a spectrum, you can, derive chemistry. And that takes us to the Habitable Worlds Observatory. And what I'll do, since NASA have done a fantastic job of getting famous Welsh actor John Rhys Davies to narrate with gravitas, I'll give you a few minutes of John's introduction.
The stars above. What secrets do they keep? One of our biggest questions has always been, are we alone? We've now discovered thousands of planets beyond our solar system, but how many of those distant worlds have the conditions for life as we know it? How many have water vapor, a beacon indicating that oceans might be present? How many have gases like oxygen and methane, possible signs of life itself? And of those, which might truly have life? After decades of asking, a future NASA telescope could bring us the answers. The Habitable Worlds Observatory is a future mission designed in the tradition of the Hubble and Webb space telescopes. It will use its unique and sensitive eyes to see planets like our own, hiding in the light of their distant stars. Astronomers could then point this mighty space observatory to the most promising planets, those that may hold liquid water. With the help of its coronagraph instrument, which blocks out the dazzling starlight, the telescope will look for undiscovered Earth-sized planets in the star's habitable zone where liquid water could exist. The light from each planet will be split into a vibrant spectrum of colors, revealing clues to the chemical signatures we seek. From there, we can attempt to discover if a planet's atmosphere contains water. And from there, other signals like oxygen or methane. Should all these signs align, the Habitable Worlds Observatory would delve deeper to reveal other hidden clues of life. With further study, we could find signs of sprawling oceans and rugged continents. And if signs of life are revealed, keep a watchful eye for changes over time. This magnificent observatory could discover dozens of worlds akin to our own in its first 5 years. The telescope will gather data on a wide variety of worlds, placing our own solar system in the context within the grand tapestry of existence. And the Habitable Worlds Observatory will, like the other great cosmic watchers, Hubble, Chandra, Spitzer, Webb, and soon Roman, also conduct a wide range of revolutionary observations of our cosmos, improving our understanding of how our universe led to potentially habitable worlds. Thus, the Habitable Worlds Observatory will help us embark on a quest as grand as any, to tell the story of life in the cosmos, and whether or not we are alone.
So that is a NASA mission, but like all the other great observatories, Europe will play a really important role. There will be one moment in human history where we transition from a species that thinks we're alone to being able to point to a star, a planet, and say there is independent life out there that comes from an independent tree of life, and we are no longer alone. And I think we're looking at the 1940s for that. And so the 1930s is clearly going to be when we'll figure out dark matter, dark energy, and inflation, right? And the 1940s is when we're going to find life on other planets. So in conclusion, I would like to say that technology is allowing us to push deeper into the cosmos at a rate that's been unprecedented in human history. In one human lifetime, we have done incredible things. We have discovered dark matter, dark energy, and inflation. And the hope with Euclid is maybe we'll actually understand them. We have, since in one lifetime, found thousands of planets outside of our solar system. And there's hope here with the Habitable Worlds Observatory that we will find life. And I'll end to remind you that I don't think discovery sits in a vacuum, that technology feeds into this, and the enthusiasm that we have to push the technology also pushes technology back into society for the benefit of everyone. Thank you very much.
Thank you. So, hello Hello, everybody. What a fantastic lecture, wasn't it?
Thank you.
And we do have time for a couple of questions. So is there anything you always wanted to know from the master of the universe? Come on, guys, questions. I see a hand there.
How much will Trump's budget impact future science?
Maybe there.
Yeah, so I think the question was, how much will Trump's budget impact the future of space science? And that's a really big question. The answer is we don't know. We're working through, so at the meeting, so the US spends an enormous amount on science and has been a world leader in sort of investing in innovation, in discovery, in a way that's unapologetic and sort of drives the world. And I think it's really inspiring, and I love working with my NASA colleagues. Having the space budget put under enormous pressure affects obviously NASA, but it affects all of us because these are now global projects. And I think we really have to understand it'll affect European science in Earth observation, it'll affect European science in exploration around the Moon and Mars, and it'll affect European exploration of the universe. So we don't know. The budget hasn't been settled, and we have to look at what the final outcome. But if the US pulls out of science in a big way, it'll have an impact on everybody, and it'll be negative.
Okay, thank you. There was a question here of a lady in row 3 or 4.
Thank you very much for that. It was fascinating. I have a childhood question, if I'm allowed to feed.
Please, yes.
And that is, what do you think our encounter with life in space will be like?
Ah, right.
And how do you think it's going to go?
Okay, very good. So I don't know, because these start us out. First of all, going from the early 90s when we didn't know of any exoplanet, we've reached a point where it looks like every star we look at, if we look hard enough, we'll find exoplanets. So planets are everywhere. We still don't know yet the answer to the question of how often does life occur, right? Are we unique or is it everywhere? And I think that'll have a big impact on answering your question. If life is rare, then the distance between us and the next one is going to be very, very far, and we'll be talking to them in the distant past, but it'll be messages back and forward. How are you doing? I'm doing okay. Great. Good for you. If it's very common, maybe that's a different story, but I think we really need to understand, and that's why experiments like the Habitable Worlds Observatory. So what it'll do is it'll find 20 best candidates, look at them really hard, and if all 20 have life, well, it's a common thing in the universe. If none of the 20 have life, that's really weird. And so I think that's what we'll have to wait and see.
I think there is a question there in the back, like 3rd row maybe.
Thanks. You said that gravity eventually wins, but from what you said later on, I got a bit confused.
Okay.
Is dark energy going to beat gravity?
Right. Well, I think that's what I'm implying. And again, not all physicists would agree. People love quantum fields. So there's a quantum field, if you like, that sort of thing, called quintessence, that could do the job of dark energy. I think my only statement is, it would be weird if when we look at the universe and 3 mysteries have popped up, and every time the standard model has been challenged, by the way, it's come from astronomy. So I'll give you an example. The standard model had embedded within it that the neutrino was massless. And now we know the neutrino has a mass and it changes flavor. That's a beyond standard model physics. That came from understanding the sun, right? That's where the initial problem came from. And so I totally get it that astronomy discovers these problems and the standard model, tweaked, gives us the answer to these problems. Except when it comes to cosmology, I just find it weird that all problems would have a standard model solution. So, if I was a betting man, and I'm not, I'd bet that at least one of these 3 is a gravity-based problem. And there are lots of gravity theories that would allow really interesting things to happen in regimes of high gravity.
Okay. Anything? I think there was somebody at the front there. No?
Yes, thanks a lot for this inspiring lecture, Professor Amara. As a space technician, I have a question regarding the Habitable Worlds Telescope. Which are the key technologies we have to master before this machine will come to life?
Yeah, it's the coronagraph. So for those of you that don't know, the coronagraph was an instrument that was designed to look at the sun. So the idea is you can point something at the sun, bring the optics to a focus, and then put a blocker that would block out the sun, and it would allow you to measure the sun's corona in great detail. Now, the idea is to point something like that at a star, so it's no longer a coronagraph, it should be called a stellar graph or something. But the idea is simple. You bring the starlight in, you put a little thing that blocks out the sun, and then you reform the image of what's left, and you should see the star. As I said, the challenge is for every one photon from the planet that you want to measure, you'll have 10 billion photons from the star. So you can imagine once those photons have entered your telescope and they bounce around the system, one in 10,000 will begin to wash out your planet signal. So getting an optical system that's that accurate and a coronagraph able to suppress at that level and stable, that's never been done.
Thanks.
I think there is somebody who's holding it.
First, thank you for your lecture. It was really interesting. What I found a little bit interesting was, I mean, I do understand the reason that we're trying to look for life similar to ours as Arabs, but I have wondered if we just focus on finding life, wouldn't it also be a possibility to also look for anaerobic life, like bacteria, since a lot of them are extremophiles, and if it's just about finding some kind of life, wouldn't that also be an approach?
Absolutely. So first of all, life like ours doesn't mean life as it is today. What the team, and there are thousands of people now working on Habitable Worlds, so if you have anybody, you want to figure out what to do with your future, this is a good thing to go into. It'll keep you in a job for a while. What the team is doing is, even if you use the Earth analog, if you look at Earth throughout its history, it used to look very different in the past, and the atmospheric chemistry is very different in the primordial Earth to what Earth is now. So that gives you a sort of template for the kind of things you could look for. But what they're really doing is just measuring, they want to measure the chemistry of a planet. And then the question is really simple. It's not, is life like what we think it is? What they want to know is, in a system without life, a planet's atmosphere will reach an equilibrium system, of where the chemicals sit. One way to think about life is it takes a system out of equilibrium, and it does weird things with the chemistry that you wouldn't expect if you didn't have, breathing organisms or whatever. And so what they're really looking for is planetary atmospheres that are out of equilibrium, and we have sort of some templates in Earth's history to look at, but any out of equilibrium chemistry would be really interesting to follow up on, including anything that might be caused by bacteria.
Okay, back there. It's complicated to see everybody of you.
Yes, a follow-up question for the detection of exoplanets and blocking the light. Would there be a use case for single photon counting and detecting the light of the planet? Or can you specify which other technology would be useful for that?
Yeah, absolutely. Single photon counting would be great. Look, what you need is to stick a coronagraph that blocks off as much of the starlight as possible. There have been ideas, by the way, in the past about flying a massive stellar shield in front of it to block a lot of the light before it even gets into the telescope. That would be massive structure in space. But yeah, when you get to the detector end, you want to measure low rates of photons, So single photon detectors would be great, and you need to measure their wavelength, right? Because you need to get a spectrum out of these things. So yeah, and the technology development for this work is happening now. The architecture hasn't been fixed. So if you want to work on that, you're welcome to.
Okay, thank you very much.
Maybe, yeah, here in the front.
Professor Amara, thank you so much for this very interesting lecture. Like, the kid in me is definitely super excited.
Excellent.
And I think my question is non-technical, is a personal question to you. And my question is there a specific vision for the far future that kind of tickles your brain? So for me personally, a vision is like when we finally have Voyager 2 back at Earth, and then we put it in a museum, and then the school kids go to see it, and they're like, oh, this is Voyager 2, and back then. So is there like something similar in your mind?
Look, I love all of it, right? So I think big experiments, the kind that I've talked about today, are absolutely brilliant, and I love working on them, and I like supporting people. I won't be driving Habitable Worlds Observatory, but there's lots of people in the UK, Germany, other places that will be getting excited, and I want to help support that. What I'm also really excited about is the small end, and this is something we looked at sort of when I looked around your lab today. Small satellites often get overlooked when we look at very exciting big $10 billion telescopes. But they're really incredible because as a physicist, I was trained in the idea that you have a theory, you go down to the basement, you fire some lasers, switch on a magnetic field, and you get the results. And then within 5 years, you've cracked whatever it is, and you move on to the next experiment. These big experiments don't have that pattern, right? They're long-term, multi-generational sort of experiments. But small sats, the kind that you work on, you can have a really interesting idea if it's really focused, bring a team together, build it really fast in a few years, get it launched, do the experiment in quantum information or whatever, and then get the results, see what you do, and then go back again. I'm actually tickled pink about small sats and what small sats, constellations of small sats are able to do, because it means we can get young people in, have them work with you on the build and see the full life cycle, and then they're very well prepared to be future PIs. So I'm super excited about small sats as well. Would you agree?
And so are we.
Yeah, of course you are.
There's somebody in the middle, approximately.
Yes, first of all, thank you for your wonderful lecture. I'm curious, the paradox of technology entering orbital space is also creating this challenge of space waste, which is actually crowding out our access to the cosmos. Where do you see development in the next years regarding space waste?
Right, yeah. And this, again, takes me back to this idea from the King about the Astra Carta, where it's an initiative to try and push us in a direction to think sustainably about space. And in economics, it's known that there's a tragedy of the commons, right? If there's a thing that we all share and nobody specifically has to pay for it, then we have a tendency as a species to abuse and let that thing kind of fall. And space, it's very easy to think of it as this infinite expanse, but our orbits around us are a finite resource that we're filling up very, very quickly. And part of it is our ability to put satellites up in the future will be limited by the space to breathe if we don't clean it up. And also, you're right, from the ground, we can't look up. So the very good example of this is radio astronomy. So radio astronomy, these giant dishes that look out, and if you look at data from radio astronomy from the 1940s and 1950s, it is beautiful. We could make these exquisite measurements of the universe. Go to a much better piece of technology now and try to make the same measurements, and you'll see that the whole thing is a mess, because we've got radio interference from everywhere. So we know this is a problem. what we've got to think about is what pushes us towards taking care of the commons. And it's not, I'm afraid, just people feeling like, let's all be nice people and help each other out. It's going to be driven by regulations, it's going to be driven by insurance, it's going to be driven by these external factors. So that's what we really have to think about. How do we incentivize and create a space ecosystem that is sustainable? Because you have to think sustainably in order to play in that arena.
Okay, there is time for 1 or 2 more questions. Maybe there at the back.
We're getting ready.
Hello, hello. Okay. So first of all, also for me, thank you for the lecture. It was really interesting. But with the Habitable Worlds Observatory being like a bit far in the future for us, because you said like the technology is a bit too advanced for us, how would you say the chances are of finding life maybe closer a bit to us on like subsurface oceans, on moons like Europa or Enceladus? Yeah. And how would you say, how far are we from sending missions to those moons and maybe drilling down and looking for microbial life there?
Yeah, great question. So let's start with Mars, because we're very close to getting to Mars. So the Rosalind Franklin rover is very close to sort of completion. So that's a rover that will go to Mars. It'll drill a couple of meters down, pull out samples, do chemistry, and look for signs of life. Now, this is likely to be ancient life, so it's kind of like an archaeological experiment into life that used to exist on Mars, and that's within the short-term horizon. The experiments around the icy moons, such as Enceladus, they're going to take a lot longer. And they're on a comparable timescale to the Habitable Worlds Observatory. They have the challenge of getting to the outer solar system. They have the challenge, do you land or do you fly by and pick up these plumes that come out of Enceladus? If you land, do you drill? Do you do chemistry locally, or do you do a sample return mission? There's still a lot of open questions. So I think these icy moon experiments will also find interesting evidence of life, and it's sort of on a comparable timescale.
Okay, thank you.
Okay, I think that concludes our questions and answers session. I think maybe there is some time later on in the reception. So thank you very much again, Adam. Thank you.
Thank you.
To stay here.
Thank you also from my side. This was really wonderful, very interesting. Thank you so much. And of course, we also have like a little present in the certificate for you. So, I don't know how to handle it.
Ooh, wonderful.
With just
Thank
one
you.
hand, so this is an orbit certificate for you. Thank
Great.
you so much.
Thank you.
And we also have some planetary sweets.
Ooh, wonderful. Thank you. Thank you so much.
So thank you so much. And for all the others who have no planetary sweets, we have now you get some other sweets and something to drink at our atrium. So please join us for some discussions, maybe about aliens, I don't know.
Wonderful.
I hope you will all come to our so-called Atrium Lichthof and see you in a minute over there. Thank you so much.
Thank you.